Good day, Dr. Dalami. We are Group 7, and today we're excited to present our operating systems project, visualization of process synchronization using the Peterson's algorithm. All right, so before we dive into the technical details, let me briefly introduce the team behind this project. So our group consists of 4 members. The first one is Guizini, Kavivartan, and myself. My name is Michelle, and Tay Sin Ying. So we have divided the work equally to bring this visualization to life. All right, so let's start with the basic. Why is synchronization so important? Modern operating systems are designed to execute multiple processes concurrently. However, when these processes request the same shared resource simultaneously without proper coordination, it leads to major system failure like race conditions, data inconsistency, and resource conflicts. So, to make this abstract concept easier to understand, we designed a relatable real-world scenario. Imagine two university students, student A and student B. They are both trying to print their assignment using a single shared printer. So in our project, the students represents the processes and the shared printer represents the critical section. So this brings us to the core problem of our project addresses. So as computer science students, we often find ourselves just like memorizing the code for Pearson's algorithm. So it is very difficult to truly understand how abstract variables like flag and turn interact, or like how busy waiting actually function in the background. So to solve this issue, our proposed solution is an interactive web-based visualization tool. So instead of just like staring at static code, our simulation allows user to see the synchronization process in real time. It displays the process states, the continuous update of the shared variables, and the step-by-step execution flow to prove exactly how the algorithm prevents race conditions. Right, I will now pass the presentation over to Guizini, who will explain our methodology and the related works behind our choice of algorithm.
Before implementing our project, we studied several synchronization methods. Peterson algorithms was selected because it is a classic software-based solution that demonstrates synchronization without requiring hardware support. Although the semaphore and mutex are commonly used in modern operating systems, Peterson algorithms is ideal for educational visualization because it clearly illustrates the concept of mutual exclusion, progress, and border wedding. Our development process consists of 6 stages. First, we conducted algorithm research and breakdown to understand how Peterson algorithms solve the critical section problem. Next, we identify key concepts including flag, turn, critical section, mutual exclusion, progress, and border wedding. Then, we map the algorithm into our real-world scenario, where process 0 and process 1 represent two students sharing one printer. After that, we designed the user interface implemented using HTML, CSS, and JavaScript. And finally, tested different scenarios to evaluate whether the algorithm satisfies all synchronization requirements.
Now I'll walk you through the system design and implementation of our project. We designed the system using a simple and modular event-driven architecture. The process begins with user interaction. Whenever user clicks a button like Request Printer, an event is triggered and sent to the Peterson algorithm logic engine. This logic engine acts as the core component of the system. It processes the user input, evaluates the synchronization conditions, and also updates the shared variable, flag, and turns. So it immediately reflects the updated stats on the interface whenever a new event occurs. To implement this simulation, we use HTML to structure the interface, CSS to design and organize the visual layout, and also we use vanilla JavaScript to implement the synchronization logic and manage the state transition. Finally, on the right, you can see our completed simulation interface. The layout is divided into several sections. On the left and right side, student 0 and student 1 representing our two processes. In the center, the shared printer represents the critical section, and it changes state whenever a process successfully enters. At the bottom, we implemented a system memory dashboard which displays real-time updates on the synchronization variable so user can observe how the algorithm behaves internally. To further visualize the execution, we also included both a current algorithm step and also execution log, allowing user to follow each action performed by the system step by step. Through this architecture and interface design, our simulation demonstrates how Peterson algorithm ensures mutual exclusion while maintaining a responsive user experience. Next, we will move on to the live demo of the simulation. Let's start with a normal single request. So I click request printer for student 0, and we can notice that the flag 0 becomes true and the turn is politely given to student 1. So because student 1 is completely idle, so the system grants student 0 for the access to use the shared printer, which is also to enter the critical section. So this successfully demonstrates our first synchronization rule, progress. The system does not artificially delay a progress when the resource is completely free. Now let's test on the rest condition. When I click on this button, it will simulate a situation where both students request the printer at the same millisecond. So now both flags are true. Student 0 sets the turn to 1, but student 1 immediately overrides it to 0. Because of this, the algorithm successfully catch the conflicts, and it forces student 1 into a yellow waiting state and allows only one student, which is student 0, to enter the critical section. This proves our second rule, mutual exclusion. The system strictly blocks a simultaneous access, completely avoiding data corruption. Finally, let's see what happens to student 1 who is currently trapped in the waiting state. So the moment I click finish and leave for student 0, the flag drops to false. So notice what just happened to student 1. Without any clicking, the system automatically detected the change and upgraded student 1 from waiting to printing. This proves our final rule. Bounded waiting. No process is starved or forced to wait forever. They are granted access the exact moment the resource is safely released. The simulation proves that Peterson algorithm satisfies all strict OS criteria. I will now pass the floor to our final presenter.
Right, so hello everyone, I'm Kavivartan from section 2, subject or operating system OS for group 7. So now let me move on to the next part, which is regarding the future recommendation. So for future work, we would suggest that the system supports multiple processes using advanced synchronization methods such as semaphores or mutex locks instead of limiting the simulation to only two processes at a time. So we would also suggest to add interactive visualization features such as an automatic animation playback and adjustable execution speed or some CPU utilization indicators to our system. So we also like to include real world synchronization scenarios. For example, like ATM transaction, database access, or ticket booking system. And also we would like to enhance the simulation to better reflect real operating system environment and improve the learning effectiveness. Next, let me move on to conclusion. So, in conclusion, we can see that we have successfully developed an interactive Peterson algorithm visualization using a shared printer scenario. We have also implemented the use of HTML, CSS, and JavaScript with an event-driven approach in this project. And this project also demonstrates how the algorithm prevents race conditions and ensures mutual exclusion, progress, and bounded waiting occurs. To add on, this project also includes graphical visualization, real-time variable tracking, execution logs, and multiple test cases for better understanding. Together, in the end, we have achieved the project objectives, and this project serves as an effective educational tool for learning process synchronization in operating system subject. And also, we would like to we would sincerely acknowledge and appreciate our lecturer Dr. Danlami and also Dr. Farkana for their guidance and teaching throughout this operating system subject SECR2043. And we are also grateful for the knowledge and support which has helped us to understand process synchronization, which directly contributed in completing this project successfully. Also, special thanks to all the group members for their cooperation, commitment, and contribution during planning the project, development of the project, testing, and also in the end, the documentation part. So, in the end, I myself, representing my group, would like to thank everyone who have supported either directly or indirectly in completing this project successfully. So, in the end, I would like to show some of the references that we used for this project. And that's all from us. Thank you for your attention.